Hello, everybody. This is Ashok Bhatt. I'm Senior Product Manager at ARM. I'm going to give a machine learning on ARM servers an update in this particular session. So just as a quick heads up, what it is being covered and what's not. Primarily, I'm going to talk about TensorFlow and PyTorch as frameworks. And within that, we'll talk about what is the end goal. I mean, why do we want TensorFlow and PyTorch on ARM servers? What's the end goal with respect to on-CPU inference? What's available today for end users, and what's being worked on to improve usability and performance, and how do you get involved? Okay. What's not being covered is the training use case and kind of ARM plus GPU, which typically is the training use case, and benchmarks and performance comparisons. So this is more of how do you get started on ARM with machine learning rather than how do you make something absolutely fast and so on. Okay. So on the CPU machine learning inference, the primary goal we have is we need to get to where other architectures are. So easy to use, best-in-class performance, inference solution on ARM servers with ML-specific CPU features. Now, we'll go through one by one what each of them mean. So when you say easy to use, what it actually means is typically a container image or Python packages. You should be able to do a pip install, or it should be part of Anaconda. And when it comes to containers, similar to what NVIDIA has in terms of the NGC, you just can pull a container image and start using it. That's the kind of easiest way for end users to get started. And then you have the popular ML frameworks support ARM as a first-class citizen. Today, all of them mostly use x86 as their primary CPU. So the goal is to get them to support ARM as well, in addition to x86. So that's the easy to use side. And then you have wide variety of inference workloads. And inference is a kind of a big continuum of workloads. We have started with image classification, but you can think of object detection, language processing like BERT models and so on. So that's the wide variety of inference workloads. And in terms of ARM architecture features, there are a bunch of ARM architecture features which have been added with machine learning in mind. So for example, we have dot product int8 option. bfloat 16 was added, and it's going to be available in Zeus family and N2 family soon. And we also have the matrix multiplier extension, which was added in 8.6, if I remember correctly, ARM 8.6 variant of the architecture, and it is part of V1 and also N2. That's going to come hopefully later this year. SVE also provides an advantage in the sense that Zeus, for example, will have a 256-bit wide vector unit, which helps typically in a machine learning operation. Okay. So that's the ARM architecture features that we're talking about. And finally, on the latest hardware. So there's a Neoverse family, which is N1, N2, V1, but we also have partner cores like Fujitsu's A64FX. So our overall goal is how do you get easy to use, best in class, high performing inference solution for ARM servers using all the CPU features. We'll go through one by one in detail later. So first, let me just cover the packages and images story, right? The ease of use of getting the container images and the packages. So in terms of ready to use packages, I'm happy to update you. I mean, last time when we talked about, we didn't have any official release. Today, TensorFlow snapshot packages are available via Lenaro. You can see 1.15 and 2.4 is available. And in terms of PyTorch, we have official support now. So if you go to PyTorch official website, you can get PyTorch 1.8 binary wheel for ARM. And similarly, you can provide the latest development wheel for PyTorch. So PyTorch happens to be the first major framework to support AR64 as a primary platform. In terms of next steps there, we still have to get to a position where TensorFlow packages are available for end users outside of things like Lenaro or community build. So think of pip or Conda, those kind of areas. How do we get the AR64 packages? Okay. So moving further on Docker recipes. Now, the Docker recipe project that we have is it's a recipe to the Docker container. So if you want to create containers of your own with various options of kind of different backends, then the Docker recipes help you. This is kind of ARM provided locations where we provide the latest and the greatest in terms of performance and enablement. So you can see two particular directories within tool solutions hosted by ARM, one for TensorFlow and one for PyTorch. Right now, they have slightly older versions of TensorFlow and PyTorch. So, for example, 2.3 TensorFlow and PyTorch 1.6. Soon, we will upgrade them to 1.8 in case of PyTorch and 2.4 or 2.5 in case of TensorFlow. So that's kind of the next steps there. The main thing as an end user is you have the Docker images itself. So last time when we spoke in September, this was still a kind of a concept. It was not available as part of Linaro Docker Hub. I'm happy to provide you an update saying that TensorFlow and PyTorch, both images are now available in Linaro Docker Hub. All you have to do is just do a Docker pull and you get the TensorFlow with all the different variants. So these are available for new version 1 right now. We will try to upgrade them to have A64FX variants and so on in the upcoming future. Plus the obvious updating the images to the newer version. Like, for example, this is also at PyTorch 1.6 and 2.3 TensorFlow. We want to upgrade them to the later version. So that's on the kind of general availability side. Quickly go to what does best-in-class performance mean for these projects. Machine learning for most purposes is collection of open source projects. So at the highest level, you have TensorFlow and PyTorch, which are the frameworks, and then there are a whole bunch of libraries which work underneath. And I've listed the important ones, but there are many, many more libraries which are important to in terms when you think about performance. The obvious ones, TensorFlow and PyTorch. TensorFlow and PyTorch, I guess they're neck and neck in terms of machine learning framework. Depending on who you ask, they will say one is more popular than the other. And both of them are similar in the sense that they have multiple backends. So for example, TensorFlow has Eigen GBP backend for FP32. So this is something that Google team themselves use. And Google, along with Intel, support OneDNN backend for x86, which has a BLAS fallback, or you can have direct kernels. So OneDNN is part of the One API family for Intel. On the PyTorch side, on the x86, you have many, many more backends. So specifically, I want to call out the FPGem backend. So this is a backend that gets used when you run quantized inference. And OpenBLAS is the BLAS backend that you fall back if you need some BLAS routines. OneDNN has also been integrated, but for example, int8 support, the 8-bit integer support is not integrated yet. So that is still pending. Whereas in the case of TensorFlow, it is already integrated. Now, the PyTorch also has backends. Like I said, it supports ARM right now as a first-class architecture. And it has two backends. QNNPAC happens to be the 8-bit integer backend, and OpenBLAS is the backend for the BLAS. Moving further, the projects that make these ML frameworks go faster. Eigen is a general C++ template library. It's a linear algebra library. It provides basic building blocks like vectors, matrices, and related algorithms. TensorFlow heavily uses Eigen for representing internal data structures and their operations. It's GBP, so there's a GBP kernel which provides the basic matrix multiplication. It's a default CPU backend for FP32. So if you're doing FP32 inference using TensorFlow by default, it goes to Eigen GBP kernel. Eigen as a project is important because it's not just a GBP kernel. I mean, TensorFlow, for all practical purposes, uses it for representing vectors, matrices, and so on. The other three libraries that I want to call out is the OneDNN library. So this is the Intel's ML open source library. It's an acceleration library. It's not directly used by the end users mostly. It's integrated with all the frameworks. So you think of TensorFlow, PyTorch, and so on. It's integrated with that. It has support for AR64. Right now it's tagged as experimental because we've just recently added. Both Fujitsu and ARM have been contributing to this project at this point in time. ARM Compute Library is ARM's open source acceleration library. So this was started with edge and mobile use cases in mind. It has a lot of high-level operators. In the future slides, you will see what exactly it has and what it doesn't and how it's being used in server. OpenBLAS is quite a common open source BLAS backend. So some of the matrix operations that machine learning frameworks use, they end up as the typical HPC style BLAS operations, and OpenBLAS happens to be very high performing in the case of ARM. So that is another key project. Quickly jumping to ARM Compute Library. This is a library which is a permissive MIT open source license. It's hosted by mlplatform.org, as I understand, and it has a collection of low-level functions for ARM CPU and GPU. When I say GPU, this is the GPUs that are typically available in mobile devices, the Mali series of GPUs, and it is used to accelerate ARM-NN, which is ARM's inference engine. Okay, so this is the solution that we had or we still have for kind of the edge use cases. How we're using it in cloud is, let me show the TensorFlow software stack. This is quite an important diagram. So let me explain this diagram. So in a typical ML inference workload, TensorFlow by default uses the gray path, which is the Eigen GBP kind of path, and you end up with the hardware. I mean, the same path is followed for even x86. What we have done is we have integrated ARM Compute Library into OneDNN in the sense that when TensorFlow calls into OneDNN, OneDNN uses ARM Compute Library operators, which have been optimized for ARM Cortex-A processors, the 64-bit ARM processors. So that's what we have done. So in other words, we have we have used our investment in kind of mobile edge devices and used the compute library to make the OneDNN, and in return, TensorFlow go fast. So even though I don't have numbers to share, so I'm happy to say that this path, the OneDNN ARM Compute Library path, is faster than the default path by a reasonable margin right now. And this is going to be hopefully default soon. Okay. So in terms of timeline, you can look at the kind of TensorFlow timeline. TensorFlow 2.4 version, which was released in December, it only had Eigen as a default path. In 2.5, which is expected end of March and it's expected in April mostly, it will have the OneDNN ARM Compute Library FP32 path. And in the future, so this TensorFlow roughly follows a quarterly cycle. So we expect 2.6 and 2.7 to end up in Q2 and Q3 of this calendar year. And within them, we will enhance the performance in the case of 2.6. And in case of 2.7, we expect also to add the bfloat16. So I'll cover the bfloat16 in more detail in the further slides. So coming to PyTorch, this is where I was talking about how OneDNN is quite good for multiple frameworks. So you can see that in the default path, PyTorch goes via OpenBLAS or QNN pack. OpenBLAS for mostly FP32 or operations where BLAS is involved, whereas QNN pack is mainly used for 8-bit integer operations. And within OneDNN, again, whatever work we have done is kind of integrated into ARM Compute Library. It did not get into the 1.8 release. The 1.8 release, which got released earlier this month, that was the first one which had AR64 support, the 64-bit ARM support. we expect the ARM compute library path to be integrated into 1.9, which we expect in next 3 to 4 months timeframe. So roughly called it Q2 calendar 21, but yeah, next 3 to 6 months. These are all ARM's estimates. I mean, we don't have an official roadmap from either the PyTorch or the TensorFlow team. So this is ARM's estimates of when the next versions are likely to come. In the future, don't know it's going to be called 1.10 or it'll be 2.0. Whenever that is, we expect also add bfloat 16. So finally, on the data type support, so this is the important bit you'll see in machine learning, where you can have the models either in FP32, or you can have it in IN16, or you can have it in bfloat 16. And I mean, it's all kinds of combinations are possible. How do you support these? And these can have a huge difference in terms of performance. They can have a huge impact in terms of performance. So let me talk through each of them. So for FP32, which is a 32-bit floating point, the most common widely used type, TensorFlow today uses Eigen as a backend. So that is kind of available. We can use it. For OneDNN ACL backend, I expect TensorFlow 2.5 to be the version which will have support for this fully. It is already available via the Docker recipes and Docker images. But if you want to really get it via the TensorFlow official packages, then official release, then it's likely to be, I mean, April timeframe that you should see this. On the PyTorch side, FP32 is already supported using OpenBLAS. The ACL path will be enabled in the next quarter. So expecting PyTorch 1.9 to have support for this. In terms of integer 8, now integer 8 is the quantization path, and the quantization path is different between ARM and Intel because of the hardware. I mean, quantization is quite hardware specific. It is not universal like FP32. So in the case of TensorFlow, today it supports TF-Lite. So TF-Lite has been designed, TF-Lite's quantization has been designed with kind of ARM in mind at the edge. That's the kind of default quantization support that is available in TensorFlow. That is available on ARM and it works well. So we have tested it on our side and it works well even on the server. So even though TensorFlow Lite has been originally aimed at edge and mobile devices, if you take TensorFlow Lite engine and if you run it on a server, we are seeing good scaling even in large core count, like 48 cores and 64 cores and so on. So if you are interested in running quantized models, I would strongly encourage you to try TF-Lite route. It's quite powerful. On the OneDNN route, one of the disadvantages of using OneDNN is OneDNN assumes quantization, which is x86 friendly. So we have integrated some operators into OneDNN that make, if you just take a model that has been previously quantized for x86, and if you try to run it on TensorFlow with OneDNN as a backend, some of the operators will fall back to ARM compute library and they'll go faster. But a whole bunch of them don't have an implementation because it's quite x86 specific. We plan to improve some of the performance in the next quarter, but broadly, we would expect end users not to rely on the kind of OneDNN path for int8. If you're doing 8-bit route, then most likely you are going to use the TF-Lite or the QNN pack, as in the case of PyTorch. So with that in segue, just going into PyTorch. In PyTorch, there is QNN pack, which is the default backend introduced by Facebook a couple of years ago. And it even though, again, like TF-Lite, even though it's been originally written for mobile, it scales really well for even server cores, large number of cores. We have tested it for 32, 48, 64, and so on. So we would recommend, if you have a PyTorch FP32 model, use the PyTorch quantization scheme, and you should be able to run it on top of QNN pack. If not, raise an issue, then we are monitoring PyTorch repo as well, and PyTorch team also potentially help in figuring out. For the same reasons I was talking about TensorFlow, we don't plan to support int8 via OneDNN route because OneDNN happens to be quite x86 quantization friendly. On the bfloat16, which is a new type, it has the same kind of, it's very, very friendly if you're going from FP32. It's the brain float format, originally developed or used by Google team. So TensorFlow, we don't have information yet on how TensorFlow is going to support bfloat16 models. However, we will use the bfloat16 model, bfloat16 type, to accelerate the FP32 model. So if you use running FP32 models on top of OneDNN ACL, which is a typical common use case, ACL does allow you to run quantization, convolution using bfloat16. So we will enable under the hood, both in case of TensorFlow and PyTorch, using bfloat16 under the hood to accelerate FP32 models. There may be a case once frameworks themselves support bfloat16, we'll allow also support the bfloat16 model. But for now, the plan is to accelerate FP32 models using bfloat16. Both of that should come in the second half of this year. Okay, so with that, let me quickly summarize where we are and where we are going. I would strongly encourage users to try the recipe images and provide feedback to us. Please, if you have any particular applications that you want to try on ARM, try the Docker images and recipes, the links that were provided in the slide deck. And there is a weekly public meeting that anybody can join meeting. The link is provided here. That happens weekly in the sense it's a bi-weekly. Every 2 weeks, we have one in Asia APAC specific time slot, and the other one happens in the US time slot. So you have kind of covering both regions, you have a meeting. Please do join that meeting, and there we can help you out with any particular issues that you're facing on ARM. With that, I'm open to any questions. That was the end of my presentation. Thank you. Okay, if there are no further questions, thanks for attending today. Hope to give you a more exciting update in 6 months' time. Bye.